Okay, everybody, you should have looked over the lecture notes before watching this particular snapshot video. First off, I'll say after looking at the lecture notes, you should be familiar with all of these particular concepts right here. You need to know these for the test. So I'm going to walk you through, first of all, some questions regarding do you actually know these terms? And so you should work out these fill in the blanks without looking at any lecture notes, all right? So I'm going to just go through this quickly here. You should work it out and then watch the video, right? Or have the video playing, stop it, work it, stop it, right? All right, so the collection of all possible outcomes of an experiment is referred to as the outcome space, the sample space, sorry. Sample space, okay? Sample space is anything and everything that could happen in the context of the experiment. An event is a subset of the sample space. An event is a subset of the sample space, okay? What I'm saying here is that the outcomes from tossing a die would be 1, 2, 3, 4, 5, 6. Those are the simplest things that could possibly happen, right? We call those things outcomes. Events are typically a little bit more complex. They consist of a combination or collection of outcomes. For example, selecting an even number. That consists of these outcomes 2, 4, and 6, right? That's what I mean by an event. It's usually, it can be as simple as an outcome, or it can be the entire sample space. But usually an event is just that, just something a little bit more complicated than an outcome. All right, but anyway, the probability of an event is always between two numbers, 0 and 1. That's based upon the definition I gave you, that the probability of an event for us is the number of ways it can occur divided by the number of ways anything can occur. So the number of ways something can occur is never negative or never less than 0, so that's why it's always at least 0. The most number of times anything could occur would be exactly how many times something can occur, right? Can never exceed the number of ways the sample space can occur. In other words, the number of outcomes you have. So that's why the numerator is never negative, but it's never greater than greater than 1. All right. When an event cannot occur, or on this one here, maybe I should be marking them. When an event cannot occur, the probability is 0. Can't happen. If an event is certain to occur, meaning it's going to happen, when I toss a die, I'm going to get a number between 1 and 6. The probability of such an event is 1. Next one. If there is a 60% chance of rain, then there's a 40% chance that it will not rain. The events rain and no rain are referred to as complements. Complements are, for you, let's say opposite. The opposite of getting a 2 is not getting a 2. The opposite of heads is tails. We denote the complement of an event by using a superscript C. The probabilities, I don't know what, that's just a typo. The probabilities of an event E and its complement are related by the following equation. An equation you should keep in mind, especially for later. That is, the probability of an event plus the probability the event does not occur has to add up to 1. The point of this being, sometimes if we're trying to find this, it could be easier to find the complement. But the thing is, once I know one of these, I can find the other one by simply subtracting from 1. Next one. The probability that is computed with the knowledge of additional information is referred to as a conditional probability. When you're given additional information, and you calculate the probability, it's referred to as a conditional probability. And the notation for that is the probability of B given A. What it's saying is that calculate the probability of this knowing or assuming the given part has occurred. Simple example. When I toss a die, my outcomes are 1, 2, 3, 4, 5, and 6, right? But if I tell you I tossed a number, but I didn't tell you exactly what it was, but I told you it was even, I gave you additional information. If it's even, you know your world now is 2, 4, and 6 because it's even. You would calculate the probability according to this new world here. So, conditional probabilities are not calculated any differently. What happens is the world might be a little bit different, right? If you remove something from the world's going to be different. Now, if you put something back, then the world's going to stay the same. And so maybe information may or may not affect what the world looks like. Okay? Two formulas that you need to know. The probability of A or B, the probability of A and B. Or means at least one of them occurs. So I want to know when at least one of these occurs. If I have an or, I can write down it as the probability of A plus the probability of B minus the probability of A and B. If I want the probability of two things happening at the same time, that's the probability of A times the probability of B given A. You just should know these formulas by heart. The easiest way to calculate a probability is by the definition. But if you can't, it might be beneficial to try one of these formulas here. Because if it's an and or an or, either one, if you look at these formulas, you're calculating probabilities of one thing happening, right? One thing happening, one thing happening. So in effect, this can be rewritten as one thing happening, which may make it easier to understand the problem and the calculations, right? Now, moving on. Given two events A, B, if the occurrence of one does not affect the probability of the other, we say the two events are independent. Independent means they do not affect one another. When I toss a die and I toss it a second time, the first toss doesn't affect the second toss, nor does the second toss affect the first toss. They're independent. And when two things are independent, the probability they happen at the same time is simply the product of their probabilities. But guess what? Notice that you have a formula for this already, right? Typically, when you get here is when you notice if they were actually independent or not, right? Because if they're independent, guess what? The world is not going to change based upon what happened. If I toss a die the second time, nothing's changed because I'm starting over. If I select a colored ball from a bag and I put it back, when I pick the second ball, the world's still the same. Independence. When you have independence, you can multiply the individual probabilities together. Next one. If two events cannot occur at the same time, we call them mutually exclusive. This means the probability of A and B happening is 0. Okay? Now we get to some probability problems. I am not going to do the math. I am just going to set it up, and then you take it from there. Okay? You have to work it out at least to a fraction. Okay? A single fraction. On a test, you don't have to reduce it to lowest terms. Okay? I'll be specific if I want a decimal number or something like that. All right? All right. We have 10,000 families. They're broken down into 4 different groups: owning a house, condo, renting a house, renting an apartment. We choose one family, and I want the probability the family rents a house. The basic definition of probability is simply how many ways can I choose somebody that rents a house? 912. How many ways can I choose somebody? There's 10,000 families. Okay, there you go. Second one, what's the probability they own a condo or rent a house? Again, I can count my way through this problem. To choose somebody that owns a condo or rents a house, well, that would be 1476 plus 912, right? The number of ways anything can happen is still 10,000. I'm only picking one. So you add your numerator, then divide by 10,000, and you'd have a decimal answer. But again, you do the math. If you add the numerators together and then divide by 10,000, you have your answer. The next example, the old colored ball in a bag problem. I have a bag. It has 3 red, 4 blue, and 7 yellow colored balls. One ball is selected and the color is noted. Now, if I tell you the ball selected is not blue, I'm giving you some information. And if I give you some information, the world might be different. And in this case, the ball is not blue. So the world now is 3 red, 7 yellow. So if I ask the question, what's the probability of getting a yellow? If I told you it's not blue, right? I told you it's not blue. The number of ways of getting a yellow is 7. The number of ways anything can happen is 10. The next one. Okay, I'll tell you right now, to get this problem here, I really shouldn't have put it on here. It's really for a later section, okay? That way I won't forget. The Centers for Disease Control reports that there were so many boys born in 2002 and so many girls. And I'm going to choose a newborn baby at random. What is the probability that it turns out to be a boy? Well, there are 2,057,979 ways of choosing a boy, right? How many ways there are of choosing anyone? Well, just add these two numbers together, right? Add these two numbers, that's your denominator. Take the quotient, round the 2 places, you got your answer. Basic definition of probability. Given A, if we want the probability it's not a boy, this is the complement that it is a boy, right? So whatever you got in A, subtract from 1. Probabilities of an event and its complement add up to 1. I'm going to end the video here because it's going on 15 minutes, so you should see another video to click on right down here. Okay?